This video is part of the series to accompany discrete mathematics and functional programming. I'm Thomas Van Drunen. In this video, I will introduce the programming content of this course. I will both explain the purpose and goals of this aspect of the course and demonstrate the most basic ideas. The demo will correspond to sections 1.6 and 1.7 in the text. I'm assuming no programming background in this introduction. If you have experience in another programming language, you might find this video unnecessary, but you'll still need to read the appropriate sections in the book. Even if you know how to program, section 1.6 will help you make sure you have the terminology straight, which will be important for our purposes. Also, it will help you identify things that are specific to the ML programming language. One way to categorize approaches to programming is to talk about paradigms, which I would describe as ways to conceptualize the program or the programming task. When people talk about programming paradigms, they most frequently have three particular paradigms in mind. The imperative paradigm, where we think of a program as a sequence of instructions to the computer. The object-oriented paradigm, where we think of the program as a collection of interacting objects, and the functional paradigm, where we think of the program as a mathematical function constructed from smaller, simpler mathematical functions. People used to characterize programming languages this way, for example, to say that ML is a functional programming language. That talk is a little dated now. The truth is that modern programming languages tend to incorporate features from all three paradigms. If you take a traditional programming course, you'll likely be taught a combination of imperative and object-oriented programming. This text strives to make up for the deficit of functional programming in computer science curriculum. There are people who believe that functional programming is simply a better way to program, and I'm not interested in the polemics of the matter myself, but I do believe that even if you do most of your programming in an object-oriented approach, such as with Java or C# or C++, understanding functional programming will help you master programming in general, and many of the lessons of functional programming transfer smoothly to other paradigms. For example, many of the object-oriented design patterns that are taught in intermediate to advanced programming courses are best understood in terms of functional programming. Moreover, functional programming is an especially good tool for illuminating the boundary and interplay between mathematics and programming. Programming languages that fit the traditional mold for being functional languages include Lisp and its dialect Scheme, Haskell, F#, and ML. The main reason I chose ML, or specifically Standard ML, or SML, for this text is its syntax. That is, its form and appearance. Its syntax is simple and particularly close to mathematical notation. The things we do here can be transferred to another functional language very easily, or to other language that has significant functional features incorporated into it. We will use ML in this course for simple programming tasks. So don't expect to produce a fancy application that you can show off with. We're pursuing the principles here. But don't let that make you think that ML can be used only for toy examples. ML and a related language, OCaml, can be used and are used for serious real-world programming as well. We will make use of ML's interactive mode. This allows us to enter short pieces of code and have the ML interpreter evaluate them and give a result. I have the ML interpreter running in this window right here, and what you see here is the interactive mode prompt. At the prompt we can enter a number or a mathematical expression, and the interpreter will evaluate it. Now we're going to use some specific terminology to describe what's going on in the programming language. And here are some important terms. Informally, a value is a piece of information. It models a mathematical idea. I won't give a formal definition of value because value is a primitive term for us. Remember that primitive terms are those for things too fundamental to define, such as set and element. An expression is any language construct that the interpreter can evaluate to a value. Thus, 21 is an expression, and it has been evaluated to 21. 4 plus 17 is an expression, also evaluated to 21. 32 minus 6 is an expression that has been evaluated to 26. More specifically, 21 is a literal. A literal is a kind of expression. It's the simplest expression that evaluates to a certain value. Or to put it more plainly, a literal is simply a value used as an expression. Looking again at what we did here, notice that we ended each expression with a semicolon. That indicates we have entered a complete expression. Had we hit enter without the semicolon, the interpreter would be waiting for us to enter more, which it indicates by a slightly different prompt. Notice that the prompt now is an equal sign instead of a dash. Now we can finish this entry into the interpreter by giving a semicolon now, and it evaluates the complete expression. Now, what's with the interpreter's response? You'll see that each time we have val it equals, and then the number that we get as a result of the evaluation, colon int. Well, val is short for value, and it indicates that this is the resulting value of the expression we entered. It is a variable. Int indicates the type of the result, and I'll say more about it and int a little bit later. Some things to note for now. ML has different symbols for subtraction and negation. The minus sign, as usual, is used for subtraction. The tilde is the negative sign. Also, as with most programming languages, multiplication is indicated by an asterisk. Division is complicated. We'll talk about that later. You'll notice that an expression itself has smaller expressions inside it, such as 32 minus 6 has the expressions 32 and 6. We could also say 14 minus 8 times 21, and that expression has the smaller expression 14, the smaller expression 8 times 21, and 8 times 21 in turn has smaller expressions 8 and 21. We call these sub-expressions. So 8 times 21 is a subexpression of 14 minus 8 times 21. The symbols for mathematical operations are called operators. The subexpressions on which the operators operate are operands. Now we're ready to talk about variables. Variables in ML act essentially as they do in ordinary mathematical notation, which should be a warning for you folks with programming experience. Variables in most programming languages work subtly but crucially differently from math variables. You may or may not have noticed. Variables in ML are closer to variables in math than variables in most programming languages are. We have already seen a variable, the it that appears after each expression that we've entered. Variables are mainly used for the reuse of something. So, for example, we can here reuse the result of a previous expression. If I type in it, there I'm using a variable, and we'll see that the result of evaluating the expression it is the same value that it had before. But now we could also say 200 plus it, and now we have the result 46. To store the result in a variable other than it, we use the following form. We say val, just as we would get from the result of entering something in the interpreter previously. For tradition's sake, let's say x equals, and I will use the previous result, it, and let's say minus 21. And now the variable x is value 25, which we can recall if necessary. Now, a little about variable names. ML, like almost any programming language, has rules for how names can be formed. Also, we should talk about variables in a larger context. An identifier is a programmer-defined name. We will see other uses of identifiers, that is, other things we will want to give names for, besides variables. An identifier is made up of letters, digits, underscores, and apostrophes. I recommend not using underscores or apostrophes because they have special uses in specific kinds of identifiers. The first character of an identifier must be a letter. Also, identifiers are case sensitive. So far, all the values and expressions we have seen have had type int. You may have guessed that int is short for integer. Indeed, if you type an expression that is not an integer, you'll see that the result is said to have type real. So, what is a type? This is in fact one of the most important programming concepts in this book. It is also our first occasion to use what we've learned in the discrete math side of things to talk about programming. A type is a set. It is a set of values associated because of the operations defined for them. In some programming languages, we may also add that how values are stored and formatted in computer memories affects how we define type. But the details of computer memory usually aren't going to be a concern for us. Thus, the int type corresponds to the set of integers we talked about when we reviewed number sets, and the real type corresponds to the set of real numbers. Here's an important point though. I said corresponds to, not equals. Perhaps a better word is models. The int type is a set of values that can be stored in a computer. It is not the same thing as the abstract notion of the set of all integers, even though it is used to model that set. And here's why that distinction is important. First of all, the int type is finite. There are only a certain number of ints that can be represented on a given computer. Here is a perfectly good integer that is too large for the int type. For reals, size isn't as big a problem as precision. Here's how we get at the predefined value for pi. Understand that this is not pi exactly. Instead, it is the closest value of the real type to pi. That is, of all the finite set of values in the real type in ML, this one is closer to pi than any other. Now, here is one way in which the details of computer memory will affect us. It turns out that ints and reals are represented in computer memory in completely different ways. So, unlike in the math view of things, the int type is not a subset of the real type. So, if we do 5.3 minus 0.3, the result we get is 5.0, which is of type real, and that is a different value from 5 of the type int. Ints and reals have different operations. Adding two reals might look the same as adding two ints. So 5.0 plus 7.0, 5 plus 7. But on computer hardware, these are different operations. Consequently, you cannot add a real and an int. A plus operation must be either an int addition or a real addition. The types of its operands must agree. If you do need to do arithmetic on data that is partially int and partially real, you can use converter functions, such as real to convert an int to a real, round that will round a real to the nearest int, floor that will round down to the largest int smaller than the given value, Ceil, short for ceiling, that will round up to the smallest integer larger than the given value. And trunc, that will simply throw away the decimal portion and thus convert a real to an int. You don't need to memorize these, as we won't use them very often. You should, however, take the time to try to figure out what the difference is between floor and trunc. In the example I've given you here, they appear to do the same thing. But perhaps if you think about what they are doing, you can think of an example on which floor and trunc will return different values. Another place where the difference between int and real comes into play is in doing division. The slash character is the operator for real division. But when dealing with integers, we often want to know separately what the integer quotient is and what the remainder is. We find these using the div operator and the mod operator. So 5 div 2 gives us 2 because 5 divided by 2 is 2 remainder something or other. Well, remainder 1, which we can get using 5 mod 2. So again, div finds the integer quotient, ignoring the remainder. Mod finds the remainder of integer division. Slash is not defined for integers. We will also see many non-numeric types in ML, mostly ones that we invent ourselves. But two common non-numeric types that are built into ML are characters and strings. A character is a single alphanumeric or punctual symbol. And a character literal begins with a pound sign and includes that character inside of quotation marks. So you see the result here is of type char, short for character. A string is a sequence of characters, and you make a string literal similar to the way that you make a character literal, but without the pound, and since it's a sequence, it can contain not just one character, but it can contain a sequence of characters. See section 1.7 for more details on characters and strings. But we also will learn more about them as the need arises. This gives you the most basic information about using the ML programming environment. In the next few sections, we will learn other bits and pieces about ML and eventually write very simple programs. But we are using the discrete math material to structure this text. So when we learn new discrete structures, that will prompt our learning new features of ML that correspond to them. The next video will consider other foundational concepts in set theory.